joints are there? Well, this is a joint, and it has 2 degrees of freedom. It's rolling and sliding. That's 2 degrees of freedom. So that's one J2 joint. We have one two-dimensional joint. So we count one of them. Okay? So this is 3, 2, 1. So plug it in there, and you will find a mobility of 1. And by the way, note, if I just restricted this to be like rolling only, which like if it was a gear, a rack on a pinion kind of thing, so it prevents sliding because of gear teeth, but it can roll, then, this would go, the J1 would go away, there would be 3 of these, and this would be a mobility of 0, and it would be a static structure. It wouldn't be able to move. It wouldn't be a mechanism at all, right? But in this case, it is a mechanism with mobility of 1. And you can imagine it just takes one parameter to define the whole thing, like 1 theta of where the egg is to lock in all the other stuff. And if I held this fixed, the whole thing would be locked up. So it makes sense it's mobility of 1. Okay, so let's look at this. Okay, this is the case. It's specifying here you can slip. So it's slipping, sliding, and rolling. So slipping and sliding are the same thing, obviously. So it has 2 degrees of freedom there. It can roll and it can slide. Okay. All right. So, first of all, you have to ask yourself again: is this a mechanism? Yes, it is. Rigid links, connected by joints, there's a ground, closed kinematic chain, and it can move, that's for sure. So it's a mechanism. All right, is it a linkage? No, it is not, because it has a higher pair. Okay, and if you have one or more higher pairs, you're not a linkage. These guys are lower pairs, but this is a higher pair. Because it's not because it has 2 degrees of freedom, it has nothing to do with that. It has everything to do with the fact that it touches at just a line or a point, and it's not surface, okay? So it's not a linkage, but it is a mechanism. All right, so let's do Kutzbach, okay? How many links are there? Well, there's 1, 2, 3, 4. Okay, how many J1 joints are there? Well, there's 1, 2, 3. This one has 2 degrees of freedom, so you don't count it. So there's 3 revolute joints there, 3 J1s. Okay, how many J2s are there? Well, I already said this has 2 degrees of freedom. It's rolling and slipping, so it's 1. Do the mobility of that, and it's M2. So it apparently has 2 degrees of freedom. Okay, so here's where, Kutzbach gives you the correct answer, but sometimes your intuition won't, because you ask yourself, how many parameters does this need to fully define it? Well, if I define this parameter, would this be fully defined without breaking the joint? Well, no, because if I locked this fixed, this guy could still rotate, and it would be sliding on this as this rotates. If this is held fixed, then this would just be sliding like a pizza cutter. So, this would be rotating, and there would be friction here. It would be sliding on that surface. It wouldn't roll with the surface. Okay, so and then you say, okay, well then it takes one more parameter to define that, and then you're good. So there's 2 independent parameters, so that makes sense. But here's the crazy thing: you could trick yourself with that trick I taught you, which is if I hold this fixed, the blue disk fixed, is the whole system locked up? Yes, it is. The whole system's locked up if I hold that blue disk fixed. So does that mean there's just 1 degree of freedom? No, this is where that is a bad way to count degrees of freedom, is you got to be careful what you hold fixed. Like this last example here, if I held this fixed, it didn't do anything. So because this acts like a structure, right? So you have to be careful what you hold fixed. In this case, the reason you can't just say, well, there's 1 degree of freedom, because when I hold this fixed, the whole thing's locked up. The reason is because by holding this fixed, you're killing both of these degrees of freedom, the sliding and rolling. If you hold the blue one fixed with respect to ground, you're killing 2 degrees of freedom by holding one fixed. And that's why that thing in your head isn't working. Okay, so you can think of it in different ways, but Kutzbach tells you the reliable, there's 2 degrees of freedom, it's mobility of 2, and yes, indeed, you'd need 2 motors and 2 independent parameters to fully define the system. Okay, so let's get to even more interesting examples. This one's not terribly interesting, but it's setting up a very interesting one. You ask yourself, what's the mobility of this? Well, they've labeled everything for you. Notice again, the ground is 1. The ground is usually always labeled 1. Okay, and so how many? And here's a bridge. So this is just all 3. That's 1 straight link. Okay, so let's count. What is n? Okay, well, it's 5, obviously. So 1, 2, 3, 4, 5. And if it wasn't obvious enough, they labeled it for you. Okay, and how many J1s are there? Well, there's 1, 2, 3, 4, 5, 6. And we don't count any of them twice. You might have, don't count this one twice. You would if there was no bridge. But since there's a bridge, these are just 2 links, so it's 1 pair. So, okay, so J1 is 6, because there's 6 revolute joints there. Okay, how many J2s are there? There's none. So you plug it in, and sure enough, mobility is 0, which is what you'd expect. You could imagine, without 5, this is basically a 4-bar. It can rock back and forth, but you put this in there, and it locks the whole thing up. So it's not a mechanism, it's not a linkage, because it doesn't move. Its mobility is 0. It's a static structure. Okay, but let's do something really weird here. What if we just changed the mechanism slightly by angling 5 so that it's parallel and the same length as 2 and 4? Now you ask yourself, how many links are there? Well, n is still 5. Okay. And you ask yourself, how many J1s are there? Well, there's still just 6. Okay. 1, 2, 3, 4, 5, 6. And how many J2s are there? There's still 0, so it's the same thing. So you plug that into Kutzbach, and it should still give you, 0. But from intuition that this is like a 4-bar. It's just there's a redundant bar in there, and it can rock back and forth just like a 4-bar. So mobility is 1, but according to Kutzbach, it should be 0. Well, and here's the real rub. Kutzbach is not always true. So that really stinks. It's very frustrating. The reason I teach it is because it's a very famous equation that can be very useful, but you have to be very careful because, all these definitions of mobility that I've given you of independent parameters is always true, but it's tough to identify independent parameters. But how many links can you hold fixed to lock it up? That's, you don't want to lay all your eggs on that basket because that can be wrong. And now here I'm telling you, even Kutzbach can be wrong, and that's true. So it's very unsettling, but it's a very famous equation, and it can largely be useful. And as long as you know the exceptions, then you can know what to look for here. So, and I know that's very unsatisfying. There's much more sophisticated, advanced mechanism theory. I've written some papers on it about how to do this for spatial 3D, very complex things to calculate the exact mobility for any situation. That's always true, but this is kind of first principles, useful back of the envelope kind of stuff. But here's, it will always be true as long as you know the exceptions. Okay, and what are the exceptions of Kutzbach? Well, look out for redundant parallel links with equal length, like this one. Always do a sanity check and see, well, does it move? Well, Kutzbach said it doesn't, So be aware of that. And then the other one is singular configurations. So this is an example of a singular configuration. Like, imagine, before these guys were in a row. So see these 3 rotations in a row, that's what makes it singular. If they weren't in a row, it would just be a 4-bar, and it could move just fine, and Kutzbach would work. It would say a mobility of 1, and it could surely move with a mobility of 1. But the second, if this is the driving one, the second I pull this down, if this locks up in a straight line, then what ends up happening is anytime you have 3 or more rotations in a row, then one of them becomes redundant. And it's called a singular configuration, and this behaves as if it's a big locked up thing. You can imagine if the motor was on this and these lined up, it would behave like a triangle, and suddenly the mobility would drop to 0. Even though Kutzbach would say the mobility is 1, because there's 4 things and 4 links and 4 J1 thing, say mobility is 1. If these guys are all in a line, it's a singular configuration, and the mobility is actually 0, and this would be locked up. Okay, so basically the exceptions to Kutzbach are kind of redundant parallel constraints that are the same length, like this one, or singular configurations where 3 or more rotations are in a row. Or also, consequently, if there's a translation, a prism joint that is perpendicular to the line of rotations, and there's 2 rotations on that line, that also is a singular thing. So if there's 2 or more rotations on a line and a translation perpendicular to it, it's singular. Or if there's no translation of prism joint, but 3 or more rotations in a line, it's a singular configuration. I know this is very confusing. I can teach you by the end of this class why this is the case, but for now you're just going to have to kind of believe it, okay? And look out for it. Okay, so Grubler's criteria. Okay, Grubler, he had it's also a very famous equation, but his is kind of more specific. It's basically doing the same thing as Kutzbach. This is Kutzbach up here that you should memorize, right? Grubler's like, okay, let's come up with an equation for just 1 degree of freedom planar mechanisms that consist of single degree of freedom joints. So he's like, look, most useful mechanisms just link one motor or one actuator to some useful output, some work thing. So we're really only interested in planar mechanisms with 1 degree of freedom. And so basically if you make this equation M1, because he's only interested in mobility of 1, and you say we're not interested in J2s, we just want single degree of freedom joints, then you get rid of J2 there, and you have this. And if you rearrange this equation, what you get is Grubler's famous equation. So it's basically Kutzbach where M is 1 and J2 is 0, and you reorganize it, boom, you get Kutzbach or Grubler's equation. So this is a special scenario, and this is more general. But I'm teaching it because it's very famous, okay? Okay, so let's look at some common planar mechanisms. Okay, so you've already looked at the 2 most common planar mechanisms, the 4-bar mechanism, but it's so common, we're going to talk about it so much in this course, you need to know some definitions here. So remember the fixed ground, it looks like there's 2 grounds, but of course there's just 1 ground, and it's always labeled 1. Okay, that's the fixed ground. The other link that's 2, usually whatever link is labeled 2 is the input link. And so that's input, meaning that's the one the motor drives. If you attached a motor here, it would be driving that input link. And then the follower link is the one on the opposite side of it. If this is the input on the left side, the follower link is on the right side. It's the one that's usually doing the work, doing the interesting thing. The whole reason the mechanism was attached to the motor was to do whatever the follower is doing. And so that's kind of the output one you really care about. Then there's the coupler that joins the 2. Okay, so there's the input, coupler, and follower. Okay. Okay, so let's look at slider crank mechanisms. The second most popular, or equally popular, is a 4-bar. This one also has some definitions. So it's got a fixed ground. It looks like 2, but there's really just 1. It's also got an input that the motor attaches to, usually the arm up at the top right or top left there. And then there's a coupler that goes down to the slider, which is usually the output. So usually you have a rotary motor that attaches to the input, and you want to translate that rotational motion to a reciprocating translation of the slider as the output. And you can see these ground points, the 2 pins here don't have to be on the same line. There can be an offset, okay, which is labeled on the right there. Okay, so it's called the offset. Okay, so now let's look at kinematic inversions in Grashoff's law. So, okay, so here's the thing with kinematic inversions. So let's take a slider crank mechanism, like the one from before. This one right here, this is a classic slider crank mechanism. It looks like there's 2 grounds, but there's really just 1. These are basically connected together. Here's the input, there's the coupler, there's the slider. Okay, so that's a classic slider crank mechanism. Okay, a critical part of the definition of a mechanism is that one of the links has to be held fixed to the ground. So in this case, it's the one labeled 1 there. Okay, which is usually always the case, right? The ground is usually always 1. Okay, what if we held, instead of grounding 1, this link here, what if we allowed 1 to move and we held 2 fixed? Which would effectively be like this mechanism. It's drawn slightly different, but you can see 1 is allowed to move and 2 is now the ground. Well, it should technically be, even though it's drawn differently, it should technically be the exact same mechanism. We just, instead of grabbing 1 fixed here, we just grab the other one fixed. and you're right, it's the same mechanism, and it has the same relative motions, but its absolute motions will be totally different. So it'll actually behave, and you can even make it look like a totally different mechanism, even though it's basically the same mechanism, the same relative motions. Okay, that's called a kinematic inversion of a mechanism. So if you have 4 links, like a slider crank does, then you can have 4 kinematic inversions. Okay, so another option is, instead of holding 1 or 2 fixed, you hold 3 fixed. That's this kinematic inversion. Or the other thing is, you can allow 1, 2, and 3 to move, but now you hold the slider, the actual box there fixed that slides, but you hold it fixed so it can't slide, and that's the 4th kinematic inversion. So the number of links a mechanism has, the number of different ways you can hold them fixed, and that's how many kinematic inversions there are. And just to repeat, kinematic inversions are the same mechanism, they have the same relative motions, but they have very different absolute motions, and they fool people into thinking they're actually totally different mechanisms. So like this one famous water pump thing here, this is basically a slider crank, except the slider is held fixed. It's actually this ground part, and link 2 here is actually the pump handle, and link 1 is what's going down into the ground, and you can see 3 is this guy right here. So it's kind of this mechanism flipped around and mirrored. It's a slider crank mechanism. Okay. So watch out. There's many different versions. Now, before I talk about Grashoff's law, you can see this is these 4 pictures are just the same 4-bar with 4 different kinematic inversions. It's 4 different kinematic inversions. The top left, you're holding that one labeled Q fixed, and then you're holding the one labeled L fixed on the top right. Here you're holding one P fixed, and here you're holding one S fixed. And you can see, even though they're the same mechanism and the relative motions are the same, the absolute motions are different. This one, the S can rotate full 360 degrees, but the P one just rocks back and forth. In this one, it's similar, but the P is rocking back and forth below. In this one, they both can rotate full 360 degrees. In this one, they both rock back and forth. So it looks like a totally different mechanism. Okay, so that's kinematic inversions. But now let's talk about Grashoff's law. So before I do that, let me tell you, one of the main purposes of mechanisms was, to do something interesting with a motor that continuously moves. So, if you caused a motor to rock a link back and forth, you'd have to speed it up and then slow it down and stop it, and then speed it up, slow it down and stop it, and speed it up, slow it down and stop it. That takes a lot of power, a lot of force. You're sloshing mass back and forth, and F equals ma. You don't want to large forces to accelerate mass and decelerate it back and forth, right? So one fix to that is, and that breaks motors, and it takes a lot of power and stuff. So one fix to that is like, hey, what you want to do with a motor is just keep it going the same speed, the same direction, continuously, forever, right? Because that's low forces on the motor. It'll last forever, or not forever, but it lasts a lot longer than rocking the motor back and forth, right? And motors just like to go in one continuous direction. So one trick is, if you attach a motor onto like a 4-bar or many other kinds of mechanisms, you can have the motor continuously rotate like this. This S link, labeled S, can just continuously rotate. But the output link, or the crank, right? The follower, link will actually just rock back and forth. Will accelerate and decelerate and slow down and stuff. So that's what a lot of people use mechanisms for, is to allow a motor to keep doing continuous motion, but like rock back and forth, okay? And so Grashoff has recognized that, and he said, okay, for a 4-bar mechanism, which is super famous, that's of course a planar mechanism, what are the conditions that allow that to occur? Because you can see for this diagram, for this particular 4-bar, yes, that S can rotate, can continuously go, 360 degrees and more, and rock that P back and forth. But for different lengths of the bars, you may actually get some configuration of the 4-bar that jam, and the motor can't continuously rotate. And so he made Grashoff's law, which basically says, when you have a 4-bar mechanism, identify the length that's the smallest, the shortest, which is labeled S in this example. Identify the length, the link that is the longest, labeled L, and add those two lengths together, and you better make sure that that sum is equal to or less than the sum of the other two remaining link lengths. Okay, so if you add Q plus P, that better be larger. And if that condition is satisfied, then this will work. So it's basically, if I give you any 4-bar and you find the shortest and longest ones and add them and make sure it's less than the other two summed together lengths, then if it satisfies Grashoff's condition, then you can attach a motor to it and it can continuously rotate and this thing can rock back and forth. Okay? Otherwise it'll jam and it won't work. And you can very easily derive this. You can imagine if that mechanism up top laid down so that S and L were in a straight line with P and Q, that's when they would be equal and it could keep going through. But if S plus L, if it's longer than that, then you can see it would jam. Okay, so to kind of convince you that's true. Okay, so now I'm actually going to stop this and do one more video for this, this topic. All right.